Imagine sending a message, maybe a secret note, and you really hope only the person it's for actually reads it. Sounds simple enough when it's just, two people. But in our huge connected digital world, this need for secure private communication just explodes. It's not just you sending an email, it's your bank, it's your smart toaster, the routers sending data everywhere, massive servers swapping critical info. Welcome to a deep dive into the, well, fascinating and often hidden world of computer network security. Today, our mission is really to unpack how our digital stuff stays private, authentic, and untampered with. We're going to explore the basic principles and the real protocols that build the secure internet you rely on, probably without even thinking about it. Think of us as guides. We'll try to demystify some complex ideas using a top-down approach, starting with the apps you use down to the actual network pipes. And this deep dive is grounded in a key textbook on computer networking, giving us a solid framework to understand the what and the why behind it all.
Exactly. And to kick things off, we often throw around the term secure communication, but what does that really mean online? It's actually more than just keeping secrets.
Okay, so beyond just confidentiality, what are the other critical parts of this security puzzle?
Well, yeah, ensuring only the sender, let's call her Alice, and the receiver, Bob, can understand the message. That's confidentiality, usually through encryption. But we also need message integrity. That means making sure the message hasn't been messed with, either deliberately or just by accident while it's traveling.
Right, so you know what you got is what they sent.
Precisely. Then there's endpoint authentication. This is super important for trust. It's about confirming Alice is really Alice and Bob is really Bob, and that neither of them is our sort of classic intruder figure, Trudy, pretending to be someone else.
Okay.
And finally, there's the bigger picture, operational security. This is about protecting whole networks, like a company's network, from broad attacks, malware, denial of service, sniffing, that kind of thing. It's the overall strategy.
That definitely clears things up. But who are the actual Alice's and Bobs needing this? Is it just us, people sending emails?
Oh, definitely not just human users doing online shopping or sending emails.
Yeah.
What's really key here is that the network itself relies heavily on these security principles. Think about DNS servers exchanging critical info securely, or routing systems sharing their tables safely. These are fundamental for the internet to even work. If Trudy could mess with those, well, chaos.
And speaking of Trudy, our friendly attacker,
Yeah.
what can she actually do? Is she just listening in?
Well, she can just listen, eavesdrop. But Trudy's often much more active. She can modify messages in transit, insert fake ones, even delete legitimate messages. And that opens the door to really serious attacks like impersonation, pretending to be you, or hijacking your connection, or just overwhelming a system so nobody can use it, which is denial of service.
Okay, scary stuff.
Yeah.
So how do we fight back? Let's get into the magic behind the defenses. Cryptography.
Indeed. Cryptography at its core is all about disguising data. You start with plain text, your normal readable message. Then, using an encryption algorithm and a secret key, you transform it into ciphertext, which just looks like random nonsense to anyone without that key. And a really powerful idea here, Kirchhoff's principle, basically says the security should all hang on the key being secret, not the method itself. The algorithm can be public knowledge.
Thinking about older methods, Julius Caesar's cipher always comes up. What was the basic idea there?
Yeah, it was super simple. Just shift each letter by a fixed number, K. So if K is 3, A becomes D, B becomes E, and so on. Easy to do, but yeah, with only 25 possible shifts, you can break it almost instantly just by trying all the keys. Brute force. Even slightly fancier ones, like substituting each letter for another specific letter, those monoalphabetic ciphers. They fall pretty easily to statistical analysis, looking at letter frequencies in the language.
So when Trudy's trying to crack these codes, what information does she usually have to work with?
Good question. We sort of classify attacks based on what Trudy knows. A ciphertext-only attack means she only has the scrambled message. That's the hardest scenario for her. Then there's a known plain text attack. Here, Trudy somehow knows some of the original message and its corresponding ciphertext. Maybe she guesses common words like Alice or log in. And the most powerful for Trudy is a chosen plain text attack. This is where she can trick Alice into encrypting messages chosen by Trudy. That gives her really useful pairs to analyze.
Okay, so those old ciphers are clearly too weak. How do modern systems deal with this and actually keep things secret?
Right. Modern symmetric systems use what are called block ciphers. They process the message in fixed-size chunks, or blocks usually 64 or 128 bits at a time. Instead of simple shifts or substitutions, they use really complex mathematical functions. Think of them like simulating huge, randomly mixed-up tables. They're designed to be incredibly hard to reverse engineer. Popular examples are DES, the data encryption standard, which used a 56-bit key now considered breakable, and the modern standard, AES, the advanced encryption standard.
AES, right, that uses longer keys.
Exactly. AES can use 128, 192, or even 256-bit keys. It's incredibly strong, not just because of the key length, but its whole structure is designed to resist known attacks. I mean, just for perspective, trying to brute force a 128-bit AES key with a machine that could crack DES in 1 second, it would still take something like 149 trillion years. It's just computationally infeasible today.
Wow. Okay, but hang on. If I encrypt the exact same block of data twice, say the same header information, wouldn't the AES ciphertext be identical both times? Couldn't that give Trudy a pattern?
That's a really sharp observation, and yes, it would. That's a potential weakness. So to prevent that, we use a technique called cipher block chaining, or CBC. What CBC does essentially is mix things up. It makes sure that even if you encrypt the same plaintext block multiple times, the resulting ciphertext looks different each time. It uses something called an initialization vector, basically a random starting value for the first block. Then, for every subsequent block, it mixes the previous ciphertext block with the current plaintext block before encrypting it.
Ah, so each block's encryption depends on the one before it.
Exactly. It creates a chain reaction, linking them all together and adding randomness. So identical plaintext blocks produce different ciphertext blocks.
Okay.
Very clever.
Okay, so for like thousands of years, secure communication needed you to share that secret key beforehand. You had to meet up, use a trusted courier, something like that. Then the 1970s happened and everything changed.
That shift was monumental. It's the invention of public key cryptography. It totally flipped the script on how we thought about secure communication. Instead of one shared secret key, now Bob has 2 keys. There's a public key, which, as the name suggests, anyone can know, even Trudy. And then there's a private key, which Bob keeps totally secret. Now, Alice uses Bob's public key to encrypt her message. And here's the magic. Only Bob's private key can decrypt it.
How does that even work? Encrypt with one key, decrypt with a different secret one.
It sounds like magic, but it's based on some really neat math. Specifically, problems that are easy to do one way, but incredibly hard to reverse. The most famous algorithm is RSA, named after its inventors, Rivest, Shamir, and Adelman. It relies on the difficulty of factoring large numbers. See, it's easy to multiply 2 huge prime numbers, p and q, together to get a massive number, n.
Yeah.
But if you only know n, finding the original p and q is practically impossible for large enough primes.
Ah, a one-way street, mathematically speaking.
Precisely. So Bob generates his primes, calculates n, and then derives his public key, ne, and private key, nd, using some specific math involving n and those primes. Alice encrypts her message m by calculating m raised to the power e, modulo n. Bob decrypts the ciphertext c by calculating c raised to the power d, modulo n. And because of the mathematical relationship between e and d, he gets the original message m back.
Okay, that's ingenious. But if RSA is so powerful and solves that whole key sharing problem, why aren't we using it for, well, everything? Why bother with symmetric keys like AES?
Great question. The main reason is performance. Public key operations like RSA are much slower, much more computationally intensive than symmetric operations like AES, especially for encrypting large amounts of data, like streaming video or big files.
Ah, okay, so it's a speed thing.
Exactly. So what we typically do in practice is use a hybrid approach. We use the slower but convenient public key crypto, like RSA, just to securely exchange temporary random symmetric session key. Once Alice and Bob both securely have this session key, they switch over to the much faster symmetric encryption, like AES, using that key for the rest of their communication for the actual data transfer.
Best of both worlds, then. Security for the key exchange, speed for the data.
You got it. Security and efficiency working together.
Okay, so we've covered keeping secrets confidentiality. But we also need to know if a message is really from who it says it's from, and that it hasn't been messed with. That brings us to integrity and authentication, right?
Absolutely right. If Bob gets a message saying it's from Alice, he needs high confidence in 2 things. 1, it really did come from Alice. 2, it wasn't altered along the way.
So how do you create a sort of digital fingerprint for a message to check its integrity?
That's a perfect analogy. We use something called a cryptographic hash function. You feed it a message, any length, and it spits out a fixed-size string of bits. This is the message digest, or hash, often written as Now, unlike a simple checksum you might find in basic error detection, these hash functions have special properties. Crucially, it's computationally infeasible, meaning practically impossible to find two different messages that produce the same hash.
Collision resistance, right?
Exactly, collision resistance.
Yeah.
It's also infeasible to find any message that matches a given hash, or to figure out the original message just from the hash. This makes it impossible for Trudy to change the message but keep the hash the same. Common examples you might hear are MD5 and SHA-1, though they have known weaknesses now, so newer versions like SHA-256 or SHA-3 are generally recommended.
Okay, so Alice and Bob have this hash function. How do they use it together to make sure the message is authentic and untampered?
They need one more ingredient, a shared secret key. Let's call it S. This is just for authentication, not necessarily encryption. Alice takes her message M, tacks on the secret key S, and calculates the hash of the whole thing, plus S. This result is called Message Authentication Code, or MAC. She then sends the original message M along with the calculated MAC. Bob receives M and the MAC. Since he also knows the secret S, he performs the exact same calculation. He computes M plus S using the received message M. If his calculated MC matches the MAC Alice sent, he can be confident the message came from someone who knew the secret S, presumably Alice, and that the message M wasn't changed in transit.
And this works even if the message itself isn't encrypted.
That's right. A common standard for this is HMAC, which stands for hashed MA. It provides integrity and authentication without needing confidentiality.
What about something more like a handwritten signature? Something that proves you sent it and you can't deny it later, something non-forgeable.
Yes, that's where digital signatures come in, and they leverage public key cryptography again, but in a different way. Instead of Alice encrypting with Bob's public key, Bob uses his own private key to sign the message. Usually, he doesn't sign the whole message, just its hash. So he calculates KBH, applying his private key operation to the hash.
Okay, so he signs the hash with his private key.
Right. Then he sends the original message M along with the signature. Anyone like Alice can receive it. She can calculate the hash herself from the message. Then she uses Bob's public key, K plus B, to verify the signature. If applying the public key operation to the signature yields the same hash, as she calculated, the signature is valid.
And because only Bob has the private key.
Only Bob could have created that specific signature for that specific message hash. So it proves authenticity, it came from Bob, and integrity. The message wasn't changed since he signed the hash. Plus, it provides non-repudiation. Bob can't later claim he didn't send it because only his private key could have created that valid signature.
Okay, that makes sense. But authenticity proves who sent it. How do I know the person I'm talking to right now is actually them, and not just Trudy replaying an old recording of them logging in, proving they're live?
Ah, yes, the playback attack. That's a classic problem. Just encrypting a password doesn't stop Trudy from recording the encrypted password and just replaying it later to log in as you.
So how do you beat that?
The solution is to introduce something unpredictable, something fresh for each session. We use a nonce, which simply means a number used only once. It has to be random and unpredictable. Here's how it works, roughly. Bob wants to authenticate Alice. He generates a random nonce, R, and sends it to Alice in the clear. Alice receives R. She must then encrypt that specific nonce R using a secret key they both share, let's say KAB. She calculates KABR and sends that encrypted nonce back to Bob. Bob receives the encrypted nonce. He decrypts it using the same shared key, KAB. If the decrypted value matches the random nonce R he originally sent just moments ago, he knows two things. One, the person on the other end knows the secret key KAB. Two, they're live because they correctly encrypted the fresh, unpredictable nonce R. Trudy couldn't have just replayed an old encrypted response because the nonce is different every time.
Clever. The nonce proves both identity via the key and liveness.
Hey.
Okay, I'm sold on public key crypto being powerful, but how do I really know that the public key I have for Bob actually belongs to Bob? What stops Trudy from just giving me her public key and saying, "Hi, I'm Bob"? I remember the textbook had this funny Trudy pizza prank example.
Ah, yes, the pizza prank. That perfectly illustrates the central problem of public key distribution. Trust. If Trudy can trick Alice into thinking Trudy's public key is Bob's, then Trudy can intercept messages from Alice to Bob, decrypt them with her own private key, read them, maybe change them, re-encrypt them with Bob's actual public key, and forward them on.
And neither Alice nor Bob would know. Bob gets the message, maybe slightly delayed. Alice thinks she sent it securely. A perfect man-in-the-middle attack.
Precisely. So how do we bind a public key to a specific identity? The most common solution is using certification authorities, or CAs. A CA is supposed to be a trusted third party. Their job is to verify someone's identity, like Bob's identity. Once verified, the CA creates a digital certificate. This certificate contains Bob's public key, Bob's identifying information, like his name or domain name, and other details. And crucially, the CA digitally signs the entire certificate using the CA's own private key.
Okay, so the CA vouches for the public key using its own signature.
Exactly. Now, when Alice wants Bob's public key, Bob sends her his certificate. Alice needs to already know and trust the CA's public key. These are often preloaded into browsers and operating systems. She uses the CA's public key to verify the signature on Bob's certificate. If the signature is valid, she can trust that the public key inside the certificate genuinely belongs to the entity identified in the certificate, Bob, because the trusted CA says so.
So you're basically shifting the trust problem from do I trust this key to do I trust this CA?
Pretty much, yes. It centralizes the trust issue.
Okay, we've built up quite a toolkit here. Encryption, hashing, signatures, certificates, nonces. Now let's see how these tools get used in the real world, layer by layer in the network stack, starting at the top.
Sounds good. And yeah, it's interesting because security features can slot in at different layers: application, transport, network, or even link layer. Each offers different advantages.
So application layer first. Let's say Alice wants to send Bob an email that's both secret and digitally signed. How does she combine these tools?
Right, this combines several things we've talked about. First, for authenticity and integrity, Alice takes her email message, calculates its hash, and then digitally signs that hash using her own private key. Then, for confidentiality, she takes the entire original message plus her signature and encrypts all of that using a brand new, randomly generated symmetric session key. Let's say she uses AES for this.
Okay, so the signed message is now secret, but how does Bob get the session key to decrypt it?
That's where public key crypto comes back in for the key exchange. Alice takes that symmetric session key she just generated and encrypts it using Bob's public key. She then sends Bob two things: the main encrypted block, message plus signature, encrypted with the session key, and the separately encrypted session key, encrypted with Bob's public key.
Got it. So Bob gets the email.
He first uses his private key to decrypt the small block containing the session key. Now he has the symmetric session key. Then he uses that session key, with AES maybe, to decrypt the main block, revealing the original message and Alice's digital signature. Finally, he verifies Alice's signature using her public key and by calculating the hash of the message himself. If it all checks out, he knows it's from Alice, it's unaltered, and it was kept confidential.
Wow, quite a process. Is there a real-world email system that does this?
Absolutely. The classic example is PGP, which stands for Pretty Good Privacy, created by Phil Zimmermann back in the early 90s. It implements pretty much exactly that flow, using standard algorithms like RSA for the public key parts, AES, or similar for the symmetric part, and SHA for hashing. PGP also had an interesting approach to certificates called the Web of Trust, where users could sign each other's keys, kind of decentralizing the trust from just CAs.
Okay, moving down one layer to the transport layer. You mentioned this is where most of us encounter security daily, like with HTTPS websites.
Exactly. The protocol here is TLS, Transport Layer Security. You might also know its older name, SSL, Secure Sockets Layer. TLS provides security for applications that use TCP. It gives you confidentiality, integrity, and authentication, primarily authenticating the server, though client authentication is also possible.
So when my browser connects to my bank's website using HTTPS, TLS is running underneath.
That's right. TLS sits between the application layer, HTTP, and the transport layer, TCP. It sets up a secure pipe before any sensitive application data, like your login or account details, is sent.
How does that TLS connection actually get set up? Seems complex.
It involves a few phases, starting with the handshake. This is where your client browser and the server talk to each other initially. They negotiate which cryptographic algorithms they both support, which cipher for encryption, which hash for integrity. They exchange random nonces to prevent replay attacks on the connection setup itself. And crucially, the server sends its certificate. Your browser uses the CA's public key to verify it, authenticating the server. They then use public key crypto, often involving those nonces, to securely agree on a shared secret value called the master secret, MS.
Okay, so the handshake establishes algorithms, proves server identity, and creates a shared secret. What next?
Next comes key derivation. Both the client and server use that master secret, MS, they just agreed upon to independently calculate a set of symmetric session keys, typically 4 keys. An encryption key for data client to server, an encryption key server to client, a mask key for integrity client to server, and a mask key server to client.
So they derive keys for both directions, for both secrecy and integrity.
Precisely. And now they're ready for the third phase, data transfer. Application data, like HTTP requests and responses, gets broken down into chunks called TLS records. For each record, a MAC-C is calculated using the appropriate MMAS key and includes a sequence number. This sequence number prevents attackers from deleting or reordering records within the secure stream. Then, the record itself plus its MSC is encrypted using the appropriate encryption key. This encrypted, integrity-protected record is then handed down to TCP to be sent across the network.
So that little padlock icon in the browser represents quite a lot of cryptographic machinery working behind the scenes.
It certainly does. Confidentiality, integrity, authentication, replay protection, all bundled together by TLS.
All right, let's keep moving down. Network layer security. What happens there?
At the network layer, the main player is IPsec. Unlike TLS, which secures specific application connections over TCP, IPsec operates at the IP layer. It can secure all IP datagrams flowing between 2 points, regardless of the application or transport protocol, TCP, UDP, whatever. It provides what you might call blanket coverage. It's very commonly used to create virtual private networks, or VPNs.
Ah, VPNs. A lot of people use those for work or privacy, so IPsec is often the technology powering them.
Very often, yes.
Hmm.
Imagine a company wants to connect its branch office network securely to its main headquarters network over the public internet. Instead of leasing expensive private lines, they can use IPsec to create a secure tunnel.
How does that tunnel work? What happens to my data packet when I'm on a company VPN using IPsec?
Okay, let's trace a datagram. Say your computer in the branch office sends a datagram destined for a server at HQ. When it hits the edge router, or VPN gateway at the branch office, IPsec kicks in. The gateway takes your original IP datagram. It then encrypts the entire payload of that datagram for confidentiality. Then, it wraps this encrypted payload in an IPsec header. One common type is the ESP header, Encapsulation Security Payload. This header includes things like a Security Parameter Index, SPI, which identifies which security settings to use for this connection, and a sequence number to prevent replay attacks. It also calculates an authentication MSC over the encrypted payload and parts of the ESP header to ensure integrity.
So it encrypts and adds integrity protection.
Right. Now, here's the tunneling part. The gateway takes this whole thing, the ESP header, the encrypted original datagram, and the MAC, and puts a completely new IP header on the very front.
A new IP header, where does that point?
This new outer header is addressed not to the final destination server at HQ, but to the IPsec gateway router at the HQ. Think of it like putting your original letter inside a secure envelope, ESP, and then putting that envelope inside another envelope addressed to the receiving security guard, HQ gateway.
The digital enchilada, as the textbook calls it.
Exactly. The routers in the middle of the public internet only see this outer IP header. They just route this big IPsec datagram towards the HQ gateway, completely unaware of the original encrypted datagram hidden inside.
And when it gets to the HQ gateway?
The HQ gateway receives it, recognizes it's an IPsec packet destined for it, based on the outer IP header and maybe the SPI. It strips off the outer header, verifies the MAC for integrity, decrypts the payload using the shared keys, and recovers the original IP datagram. Then it forwards that original datagram onto the internal HQ network towards the actual destination server.
That's really neat. And all the keys and algorithms for this are managed through something called a security association.
Correct. An IPsec Security Association, SA, is the set of parameters, algorithms, keys, key lifetime, sequence number counters, agreed upon for a unidirectional IPsec connection. So a typical VPN tunnel would have at least 2 SAs, one for each direction. These SAs are stored in a Security Association database, SAD, on the gateways. And for larger setups, establishing these SAs and their keys automatically is handled by a protocol called IKE, the Internet Key Exchange.
Okay, fascinating stuff. Finally, let's hit the bottom layer. We're covering the link layer, specifically wireless. You said sniffing is easiest here.
Yeah, because wireless signals inherently broadcast through the air. Anyone nearby with the right antenna could potentially pick them up. So security here is absolutely critical. Both 802.11 Wi-Fi and 4G, 5G cellular networks have built-in security mechanisms for authentication and encryption. A key concept here is mutual authentication. Your device needs to prove itself to the network, and the network needs to prove itself to your device.
Let's talk Wi-Fi first. I remember the old WEP standard was notoriously bad. What replaced it?
Oh, WEP was fundamentally broken. Its cryptographic design, especially how it used keys, made it relatively easy to crack with readily available tools. Don't use WEP. It was replaced by WPA, Wi-Fi Protected Access, and then WPA2, which became the standard for a long time. WPA2 mandated the use of strong encryption, specifically AES, which we talked about earlier. More recently, WPA3 has been introduced with further security enhancements.
How does WPA2 or WPA3 actually set up the secure connection when I connect my laptop to my home Wi-Fi?
At the heart of it, when you connect using a password, what's technically called a pre-shared key, or PSK, there's a process called a four-way handshake. This happens between your device, the supplicant, and the authenticator, usually your Wi-Fi access point. They use your shared password, along with exchanging nonces and calculating AMSIs using HMAC, to mutually authenticate each other and, crucially, to derive fresh temporary session keys for encrypting the actual Wi-Fi traffic data frames between your device and the access point.
So similar principles to TLS and IPsec use a shared secret or certificates, exchange nonces, derive session keys.
Exactly. The core cryptographic primitives are applied in different ways and different layers.
And what about our phones connecting to cellular networks like 4G or 5G?
Very similar concepts there, too. Cellular networks use protocols called authentication and key agreement, aka. There's a long-term secret key shared between your phone's SIM card, or eSIM, and your mobile operator's database, the Home Subscriber Service, HSS. When your phone connects to a cell tower, it engages in a challenge-response protocol with the network involving that shared secret, nonces, and cryptographic functions. This process achieves mutual authentication. The network verifies your SIM, and your SIM verifies you're talking to a legitimate network. And as part of this AKA process, they also derive temporary session keys for encrypting your voice calls and data traffic over the air interface between your phone and the cell tower base station.
Does 5G change much in this regard?
5G enhances security in several ways. It offers more flexible authentication methods. It also puts a stronger emphasis on protecting your long-term identity, like your MSI, International Mobile Subscriber Identity. In older networks, this could sometimes be sent unencrypted, creating privacy risks. 5G aims to always encrypt it early in the connection process.
Okay, great. So we've secured communications at multiple layers, but what about protecting an entire organization's network? Defending the perimeter from the dangers of the open internet.
Right. That takes us into operational security, and the two main tools here are firewalls and intrusion detection prevention systems, IDSES. The basic idea of a firewall is to create a controlled boundary between your trusted internal network and the untrusted external network, the internet.
What's a firewall actually doing at that boundary? Is it just blocking stuff?
It's essentially acting as a traffic cop. A firewall is usually a dedicated device or software that all traffic entering or leaving the internal network must pass through. Its goals are: 1. Enforce that all traffic goes through it. 2. Permit only authorized traffic to pass based on the organization's security policy. And 3. The firewall device itself must be hardened against attack.
How does it decide what traffic is authorized? What kind of rules does it use?
There are a few main types of firewalls based on how smart they are. The simplest are traditional packet filters. These are often called stateless filters. They look at each incoming or outgoing IP datagram in isolation. They examine header information like source-to-destination IP addresses, source-to-destination port numbers, protocol type TCP/UDP, maybe TCP flags like SYN or ACK. They compare this information against a set of rules, often called an access control list, ACL. Rule examples might be: block all incoming traffic destined for port 23, Telnet, or allow outgoing traffic from any internal IP address to any external address on port 80, HTTP.
Stateless, meaning they don't remember past packets.
Exactly. They don't keep track of ongoing connections. This can be a limitation. For example, a stateless filter might allow any incoming packet with the ACK flag set, assuming it's part of an established TCP connection. But an attacker could craft fake ACK packets to try and probe the network.
So what's the next level up?
Stateful packet filters. These are much more common today. They do keep track of ongoing TCP connections. They maintain a connection table. When an internal user initiates an outgoing TCP connection, sending a SYM packet, the stateful firewall records that connection attempt. Then, when the return packet, SYN-ACK, comes back from the external server, the firewall checks its table. If it sees the packet matches an existing legitimate connection initiator from inside, it allows it through. This is much more secure because it only allows incoming TCP traffic that is a direct response to an outgoing connection request. It can block unsolicited incoming SYN packets or fake ACKs much more effectively.
Okay, stateful makes sense. Is there anything even more sophisticated?
Yes, application gateways, also sometimes called proxy firewalls. These operate at an even higher level. They don't just look at IP and TCP headers. They understand specific application protocols like HTTP, FTP, or SMTP email. They act as a proxy or intermediary for specific applications. All client requests go to the gateway, which then makes a separate connection to the actual server on the client's behalf after potentially performing deep inspection or requiring specific user authentication.
So they can enforce much finer-grained policies based on the actual application content or user identity.
Exactly. For example, an HTTP gateway might filter out known malicious websites or scan downloads for viruses. A Telnet gateway might require username password authentication at the firewall before allowing any connection out.
Okay, so firewalls are primarily about blocking unauthorized traffic based on rules. But what if something malicious does get through? Or what if we want to detect attacks that firewalls might miss or even stop them actively?
That's precisely the role of intrusion detection systems, IDS, and intrusion prevention systems, IPS. These systems go beyond basic firewall rules and perform deep packet inspection. They look inside the data payload of the packets, searching for signs of malicious activity.
What's the difference between IDS and IPS?
An IDS simply detects suspicious activity and generates an alert, logs it, sends an email to the admin, etc. It's like a burglar alarm. IPS, on the other hand, sits in line with the traffic flow and can actively block or prevent the detected malicious traffic from proceeding. It's like a security guard who can tackle the intruder.
How do these systems know what counts as suspicious or malicious?
They generally use two main approaches. The most common is signature-based detection. These systems have a large database of known attack signatures. A signature is basically a pattern that matches known malicious traffic, maybe a specific sequence of bytes found in a known worm, or a particular pattern of port scanning activity. Snort, a very popular open-source IDS IPS, relies heavily on signatures.
The downside being they can only cache known attacks, right? What about brand new ones?
Correct. That's where the second approach comes in, anomaly-based detection. These systems try to build a model of what normal network traffic looks like for your specific network over time. They monitor various statistics, traffic volume, connection rates, protocols used, packet sizes, etc. Then, if they detect a significant deviation from this learned baseline, they flag it as anomalous and potentially malicious.
That sounds powerful for catching new attacks.
It has that potential, yes. But the big challenge with anomaly detection is tuning it correctly. It's hard to define normal perfectly, and network traffic can vary legitimately. So these systems can sometimes generate a lot of false positives flagging legitimate traffic as suspicious, which can be noisy and time-consuming for administrators. It's a trickier balancing act.
Wow. So we've really covered a lot of ground. From the basic need for secure messages all the way through encryption, authentication, and how we apply these tools across the network stack, right down to firewalls and intrusion detection guarding entire networks.
We really have. I think the key takeaway is that network security isn't just one thing, it's a layered defense. It involves applying these fundamental cryptographic principles, confidentiality, integrity, authentication, consistently at multiple points in the network architecture. It's a constant cat-and-mouse game against attackers.
It makes you appreciate what's happening behind the scenes. I like that quote you mentioned earlier from Stephen Bellovin, a real pioneer in this field. He said something like, "Learning the mechanisms is the easy part. Learning how to think paranoid is harder."
Yeah, and he added, you have to remember that probability distributions don't apply. The attackers can and will find improbable conditions, and the details matter a lot. It really speaks to the mindset needed, always thinking about how things could break or be exploited.
He also pointed out something crucial, that most security problems are due to buggy code, calling it the oldest unsolved problem in computer science.
That's such an important point. Even with perfect cryptographic algorithms, a simple implementation error, a buffer overflow, or a flaw in how keys are handled can completely undermine the security. It highlights that robust implementation is just as critical as sound theoretical design.
So hopefully the next time you, our listener, click a secure link, send an email, or just connect to Wi-Fi, you'll have a bit more appreciation for all those hidden layers of defense working tirelessly to keep your digital world safer. It's clearly a complex field, constantly evolving to stay ahead of new threats, always pushing the boundaries to secure our incredibly interconnected world.